Hello, welcome to the trenches of cosmology. So, normally I start by saying that here in the trenches of cosmology, the goal is to give you an idea of what it is that the cosmologists are working on in the present tense, what we find interesting. But today we'll be trying something slightly different. We'll be doing a more, I don't know, orthodox outreach science communication sort of thing and talking about the some commonly asked cosmology questions that I see all around. So, we'll have a go at answering them. The hope is that maybe by talking about them live, people who have questions can ask them live and get a feedback on those sorts of ideas. As per usual, though, I'll start at the beginning, just as people come in, by going over some of the recent most popular papers in journal clubs. So, if I get this right, and then I want to be in the background somewhere. No. Okay. And then I want to swap me and that around. So I want that to be a number one. I think that makes sense. Yeah. So what this is a website where cosmology journal clubs can run their journal clubs. And then people who are attending these journal clubs can vote to discuss these papers. And if they want to discuss them, they vote for them. Hold on, I'm just going to make it so that I can see that as well because it's quite small on my screen now. I was having trouble sharing screen in the past, so I've made it an image. And because I've made it an image, the Hat Studio makes it very small. Okay, now I can see it. So this is where people they vote for whether they want to discuss papers, and by logging out of any journal clubs myself, I can then see how many votes papers have gotten over all journal clubs. So the the papers here are the most voted for ones. The top one this week is actually it itself is maybe not so interesting, but it's part of maybe an interesting story. But what these guys, Bicep slash Kick, have been trying to do is measure a certain signal in the cosmic microwave background, which is called B modes. Um, that is it's a signature in the polarization, and it would be present if there were primordial gravitational waves. So as it says, improved constraints on primordial gravitational waves. So yeah, this would be a very, very interesting thing if they did detect it, because it would be evidence that this thing called, probably this thing called inflation happened if we detected primordial gravitational waves. And the interesting story here is that, when was it? It was probably around about 2012, because I was in Sussex. No, that'd be 2014. The predecessor to these guys, to Bicep Keck, so just Bicep, actually announced a discovery of these B modes, and therefore primordial gravitational waves, with an amplitude that actually matched quite a popular model of inflation at the time. And so that was huge news. But it turned out that they were just seeing this effect of dust in the Milky Way galaxy that was polarized in the same way that one would expect the CMB to be polarized. So this is why now they use Planck and WMAP as well as just their own ones. They use those other telescopes, Planck and WMAP being two telescopes that were in space. Planck being the more recent one, and WMAP being an earlier one, because they have more coverage of frequencies. So they can see multiple frequencies, and then you can use that to see how the signal you're looking at changes with frequency. And that allows you to, because the dust signal, despite being similar in magnitude, changes with frequency differently to how the cosmic microwave background signal would change, and therefore you can tell the difference between the two types of signals. Unfortunately, now in 2021, all Bicep are getting, all anyone is getting, are upper bounds. There's no actual evidence of this B mode polarization. particular polarization signal that would be evidence of gravitational waves. So that doesn't mean one has ruled out inflation, because essentially inflation predicts that there should be these primordial gravitational waves, but as a paradigm, inflation doesn't tell you what their magnitude should be. Different models of inflation will tell you what the magnitude should be, but they don't all have the same magnitude. It essentially depends on the energy scale during inflation. Yeah, it doesn't in the hi Paul. It doesn't in the present tense. Hydrodynamic doesn't refer to. I'll share your message on screen when I get to that paper, which I'll get to in a second. So yeah, there's not that much really to write home about anymore, except that this upper bound is gradually dropping, and that does rule out certain models of inflation. But there are very compelling models of inflation that predict that this signal should be so small that BICEP will never observe it. And I mean, there are compelling models where essentially it'll never be observed. Although one should always be careful about saying something should never be observed, because technology will just get better and better and better, and maybe a few centuries from now it's being detected. Yeah. So let's move to number 2. And Paul asked the question, wondering if hydrodynamic refers to water. I'm not sure. So last week we actually had a guest talking about their work with simulations that are hydrodynamic simulations, and I think it comes from the idea that when you're simulating water, you have things like pressure, whereas in normal, or maybe not normal, but vanilla gravity simulations, you don't have pressure, you just have gravity, and you have material in your universe that is interacting under gravity. But then when you get to very small scales, you do need to add pressure, because you have hot gas that is doing all sorts of stuff that can only be done if it has a pressure. And I think that's where the word hydrodynamic comes from, including pressure, but not including water. So here, the thing that is being simulated is hot gas, mostly hydrogen, but then after secondary effects like supernovae and things, it'll turn into other stuff as well. Anything that comes out of a supernova. So all of the elements of the periodic table to different proportions, and they have pressure, and when they start to cluster, they'll heat up and things like that. And so you need to simulate the pressure equations as well, which is where the hydrodynamic, and I guess magneto means that they're simulating magnetic fields as well, and radiation meaning that perhaps also as that hot gas is heating up and it's giving off radiation, they're actually including the effects of that radiation. So this looks like it's I'd never heard of Tessan before this paper, because as you can see from the first word, introducing, this is not something that's been around for a while. But what's important about the rest of this title is the epoch of reionization. So this is a crucial period of relatively recent in the universe's history, when enough stars existed that all of the neutral hydrogen that was otherwise just kind of floating around in space, hadn't yet fallen into a star or anything like that, is ionized. So the star's energy is enough to hit these neutral hydrogen atoms and knock the electron off. And then once it's knocked the electron off, the universe is in a sense ionized. And for once, cosmology, with its recombination, and there's another somewhere, reheating and inflation, and recombination meaning when the electron binds to the proton, and essentially when the CMB gets formed, and reheating meaning after inflation, when the universe heats up. The reason those two words are really bad words is that there's no evidence, certainly for recombination, that hydrogen and protons and electrons were ever bound. So they're not recombining, they're combining for the first time. And with inflation as well, there's no evidence that the universe was, prior to inflation, in a very hot state. So the reheating after inflation is also a bad word. But for once we have a word where reionization is grammatically valid, because you have this ionized plasma before the CMB forms, so in the very hot early universe, when protons aren't bound to electrons, and then it cools enough that they do get bound, and then for a long period of time the universe is neutral, and then stars form and they give off enough energy that the hydrogen reionizes. And this is very, very important, because I mean, as one might naively guess, because a neutral universe, light propagating through it is going to be very different to a charged universe with light propagating through it. So I've mentioned on this stream, not this particular stream, at this channel, whatever one calls it, a few times, these fast radio bursts that are really quite useful for a bunch of things. But one of them is measuring distances, that you can measure the distance to a fast radio burst, because the light coming from the fast radio burst, the radio frequencies get dispersed, that different frequencies travel at slightly different speeds through the intergalactic medium, which is high ionized hydrogen. But prior to reionization, that wouldn't happen. But also the CMB scatters off these electrons, and that has an effect on the. I mean, yeah. Let's just bring it up. Hopefully it goes to number one. This guy, the plot that has the most information in cosmology about how different scales have interacted. I'm not going to go into detail today about what this plot is, but it's the amplitude of fluctuations in the cosmic microwave background at different angular scales. You see on the bottom, you've got an angular scale, but reionization affects that. So let's see if we can go back to where we were. No, I messed that up. And get rid of the CMB like that. Good. So yeah, reionization affects the CMB. So it's very crucial to know when it happened and at what rate it happened. So the fact that it includes a bunch of effects that aren't just gravity, you need to have the right star formation rate so that you know how many stars are being formed, so you know how much light they're giving off. You need to know how they then interact with the neutral hydrogen at what rates. Then when the neutral hydrogen is starting to form, you need to know how, I guess, clustered the neutral hydrogen is. And all of that means that simulating this is a very difficult thing. There have been simulations in the past of it, so I'm not sure exactly what is new in this, other than perhaps just 2021 computing power makes it even more powerful and able to be simulated. But it's a super important thing to be simulating and predicting this reionization. When Planck produced the results, I'm going to go back to that plot I just took off, but this one, when you see the theory curve here, which is the green one, the one that is quite a wide curve at the very large angular scales and then becomes a very precise curve at the smaller angular scales, that is fitting to this data with a certain number of free parameters. Now, some of these are very fundamental parameters, like the density of dark matter or the overall amplitude of the actual fluctuations in the primordial universe, or the amount of non-dark matter or the amount of dark energy. But one of the parameters is actually a very phenomenological parameter, and it is essentially when the time, the redshift or distance away from us, time when this reionization happened. So it's essentially the only phenomenological parameter that goes into producing this final prediction curve here. And it shows how important this is and how difficult it has been to predict, that all the other things are fundamental things, like the expansion rate of the universe and the density of dark matter. But this one, the time when reionization happened, is in principle predictable. It's not something that we don't know, but it's so difficult to predict that it comes into these simulations and things. So yeah, reionization is important, and that's why 41 people, and more than almost anything else, wanted to talk about it. So let's see if we can get rid of that. Slowly getting the hang of moving around in HAPS. Okay. The next one is, cosmological constraints without fingers of God. So I can imagine that someone who doesn't know cosmology finds that extremely interesting. Fingers of God, what has God got to do with cosmology? So I should have drawn a quick picture for this, but I didn't, because I was just reading through these papers this morning. But the fingers of God are a data effect that makes your results look like you've got this kind of finger. So it's got nothing to do with a god, as perhaps one would have guessed. But okay, for us to know how far away something is, we have to measure its redshift, its Doppler shift. And then from the model of the universe, we know that if it is moving away from us at a certain speed, it is a certain distance away. Distances are really, really difficult to measure, which is why this Hubble parameter, this expansion rate, is such a difficult thing to pin down. I've mentioned this a few times in streams. Uh, so most of the time, when you're trying to say how far away is something, you're just using its redshift, its Doppler shift. But there's a big problem in that, which is that if you're measuring stuff inside, let's say, a galaxy or a cluster of galaxies, their bulk flow is maybe moving away from us. Well, that's moving towards you and the camera, moving away from the camera towards me. But inside, everything's kind of moving around and orbiting and doing all sorts of complicated motion. Now, most of the time, that motion is not large enough, or it's not in the right direction to bias your measurements too much. So I mean, if you've got if you're trying to measure the expansion from something moving in this direction, so away from you, but something's orbiting in this direction, it's not going to have a massive effect on your measured Doppler effect. But if you have something literally along your line of sight falling into a gravitational well, a galaxy or a galaxy cluster, or something climbing out, then you get a very, very strong shift in the Doppler effect because it's moving relative to its galaxy at quite a large speed. And therefore, when you use those measurements to infer how far away that galaxy is, how fast it's moving away from you, and therefore how far away it is, you get a bias. So then what you see is that if you're looking at a galaxy or a cluster of galaxies and you measure uh, this distance that stuff is away from you via the Doppler effect, that at most angles it's not too big of a problem, but directly along the the line of sight, so that things are moving through the center of the galaxy, you get a very large distortion. And then that looks like a kind of like a finger because it's so narrow and it's directly along that line of sight. So what these guys have tried to do is find a way to, I guess, essentially not. So then modeling this modeling the fingers of God in a angular. Wow, trying to yeah, they found a clever way of modeling that effect that makes it easier to remove from your analysis. I don't think I want to go into more detail than that. Okay, then 5 is also this Thesin project and more details about the intergalactic medium, so the stuff between galaxies and things like that. 4, um, so we talked a little bit last week about dark matter halos. These are these things that are like the blobs of dark matter around gravitationally bound stuff like galaxies that we can see. Uh, when we do simulations of dark matter only objects, they the density profile. So what a density profile is the measurement of the density as you move away from the center. So you get a function of the density as a function of the radius that you're looking away from the center. They tend to follow this relatively universal profile called an NFW, a Navarro Frank White, because they were the first people who ran the simulations and discovered this profile. That has only a few parameters that go into it, but it's not perfect. Every actual dark matter profile will have some scatter around it in your simulation. So what these guys have done is they've introduced a new parameter that tries to quantify this deviation and make it more universal, so that if you measure certain properties of a dark matter halo in your simulation, you can predict the deviations that you expect to see away from this NFW profile. And that's obviously super useful because if you in the real world can measure these properties and say, therefore, I know what the dark matter density profile is of a real world density halo, dark matter halo, sorry, out there in the universe, then that's great, right? Because you can measure you can predict certain things, and like for example, lensing. If you know exactly how the dark matter is distributed around the central area, then you know how the light from behind it will get lensed as it travels through the universe. And you want to have as precise as possible prediction of how things get lensed, so that then when you see how they've been lensed, you are constraining your cosmological models and things like that. Cool. So let's move on from that. I guess no new questions. Right. So the first thing I was going to try and tackle is this question of what is the universe expanding into? And I see, Paul, you asked a question prior to the stream. Thanks for that. Saying, is there more reason to believe the universe is finite or infinite? So I guess we'll get into that in answering what is the universe expanding into, because it comes up in the context of that quite naturally. So one of the reasons I wanted to tackle this question is I find some of the answers given by other cosmologists not wrong, but kind of, I don't know, misleading perhaps, or overly they present speculative stuff as more correct than it is. But I mean, a lot of the more popular or more well-known science popularizers are notorious for doing that. So anyway, so before saying what is the universe expanding into, I think I'll talk for a while about what we mean when we say expanding universe. So it's very popular for people to talk about space itself expanding, and that's not wrong, but it isn't the only way of thinking about it, and it leads to some misconceptions. So what is true is that, and this is the only thing that's like factually completely accurate, is that stuff is moving away from other stuff. The things that we can observe, galaxies, are moving away from us, and they're moving away from each other. You can interpret that as the space between them expanding, or you can interpret it as the laws of physics causing them to move apart. And so, yeah, this idea that there must be space in between them coming into existence to cause them to expand, I think is very misleading, because it makes it seem like space is a thing that is being created, when it's in reality you just have space-time and things moving around in space-time. There's not space being made or destroyed. And so we know that the universe is expanding in a couple of ways. First of all, when we can measure distances, the further away we see, the faster things are moving. So that shows us that not only is generally everything moving away from us, but everything's moving away from everything else. And I've made a figure that I'm going to try and use to explain how the expansion means that everything is moving away from everything else. That it's not just that we're like in the center of some bubble and everything's moving away from us, but it's not. But it's not that everything else is moving away from everything else. When we look far away, we see how the universe was in the past, and this is simply because light takes a finite amount of time to reach us, right? Like we're not seeing millions of light years away or billions of light years away how they are today. We're seeing how they were billions of years away ago. And so when we look further away, things are more dense. The local environments are more dense. There's more stuff inside a finite volume when we look further away. So this is also indicating that the universe is expanding, that stuff is getting further apart from each other, because in the past it was closer together. Then there's the sound waves in the CMB and all of this that shows that in the distant past there was this hot plasma of protons and electrons that formed the CMB that had sound waves in it, and that essentially shows that when the CMB was forming, the universe was so dense, everything was so close together that hydrogen was no longer bound. The electrons weren't bound to the proton. And then the final piece of evidence that the universe is expanding, in other words, was more dense in the past, is the relative abundances of hydrogen, helium, and lithium in the universe. So if you rewind the universe even further back than the cosmic microwave background, when hydrogen wasn't bound, you get to the point where nuclear physics becomes relevant, where protons and neutrons would not be bound inside of a helium nucleus, and the quarks would not behave as bound quarks. They would behave more like they'd have enough energy to kind of be moving around a little bit. And then if you run the universe forwards, you get a prediction based on, you have to put one number in, which is the radiation to matter ratio. How much, and this dictates how fast the universe is expanding, given how much, well, not hydrogen, but quarks and protons and things are around. And so if you run that forward, you get a prediction for the nuclear physics that'll happen, that as the universe is expanding and it's becoming cool enough for something like hydrogen to form and for something like helium to form, depending on how fast it's expanding and how fast it cools, you will get different ratios of hydrogen and helium and lithium, because you will get different nuclear physics reaction rates. And it so happens that the relative abundances of hydrogen and helium and lithium match what we would expect for a I should probably have myself on full screen now, for what the early universe would look like if it was once in this hot dense state. So that's the evidence we have that the universe is expanding, and what one means when one says that the universe is expanding. But we can't see further back. We can't see further back than the CMB, and we can't directly infer further back than the epoch of nuclear physics, when hydrogen, helium, and lithium were being formed. We did briefly talk about this bicep result earlier, where they're measuring this polarization in the CMB that would allow one to detect the evidence of primordial gravitational waves. So if there were primordial gravitational waves, we would be able to infer even further back, and that would be very exciting. And then one might start to be able to answer even further back how large the universe is. But at the moment, we can only see a finite time further back, which means that because light travels at a finite speed, we only see a finite distance further back. So then I've kind of prepared an image for this. So I am not a great drawer, so I apologize if this isn't as clear as I might want it to be. Let me just also get it up again on my screen so I can see what I'm talking about. I think that was one. Yeah, so what I've drawn here is a kind of picture of what I've just been kind of talking about. At the center of the circle, I've drawn us. And then around us, I've drawn a circle saying edge of observable universe. So as far as we know, the edge of the observable universe is expanding into more universe. We can see what it was like in the past when it was smaller, and we can see what it is like now. And between then and now, it has expanded, and it has expanded simply into more universe. As time goes on, we can see a further distance away, and the rest of the universe looks like the local universe. So to say what is the universe expanding into, all we know is the observable universe. And so the answer to the question of what is the observable universe expanding into is more universe. Now, I appreciate that that's probably not particularly satisfying, and that one is thinking, oh, no, but when I ask the question, I mean like the whole universe, not just the observable universe. What is the whole universe expanding into? Well, the answer to that is it could, in a sense, be anything. So as I've drawn in this picture, the area outside of this is unknowable. Maybe the universe looks like this weird outline I've drawn here, or maybe it's infinite. If it's infinite, it can still be expanding and not expanding into something. And I've got another picture that I think maybe gives an idea of what that is like in a second. If it is not infinite but finite, well, it depends what one means by the universe. The thing that is expanding in the universe might be finite and might have some edge, and outside of that, there might be stuff moving inwards. There might be a what would be called a phase transition. The behavior of the matter inside the universe outside of this expanding piece might be different. Masses of objects might have different values and different interactions that mean that it's not expanding. But we simply don't know because all we can see is the observable universe, and as far as we see it is expanding into more universe. And the other option is that the universe is in some way uh, finite in its total extent, and there's nothing outside the expanding region. And then you would get situations where maybe it repeats, where if you travel far enough in one direction, you come back to where you came from. And there, I think that is the one where it perhaps feels least satisfying. That I would sit here and say it's not expanding into anything; it's just expanding. But it's possible to write down the mathematics of geometry where you have a finite sized object, and it doesn't have to be embedded in anything. It could be all there is. And yeah, getting all worked up about the idea that it must be expanding into something is again because you're thinking of there being this uh, space that is getting bigger rather than there's just stuff that's moving apart and getting less dense. And there, if you have a finite repeating thing, things can just get less dense. So I want to talk about this idea of an infinite thing that is expanding, or yeah. So again, apologize for my artistic skills, but what I've drawn here is a one. No, I haven't. What I've drawn here is a one-dimensional uh, toy universe. So let me again just make sure I can see it in relative sizes. So what I'm trying to get across in this picture here is, let's say the universe is one dimensional and A, B, C, D, E, F, G, I, J, K, L, M, N, O, P, Q, R are, so looking at the top row for now, are the locations of galaxies in the universe. And for this toy universe, they're all equally spaced objects. And then sometime later, we move to the second row, and the way I've drawn this thing is as if it's centered on H. So instead of being hello Arthur, instead of being I being 1 unit away from H, it's now 2 units, and J is now 4 units away from H, and K is now 6 units away from H. And this is what the expansion of the universe looks like in a sort of toy one-dimensional sense. And then another unit of time later, on the third row, we now have I being 4 units away from H and J being 8 units away. So the idea behind what I'm trying to show here is that even if this top row extended all the way to infinity in one direction and infinity in the other direction, it's still possible that over time objects can get further away. The things that are off the plot here would still be getting further away. And and the thing I want you to take away when looking at this is it doesn't have to be centered on H. If I was instead to have treated myself, no, between each letter there's just a finite distance. So between H and I there's a finite distance. Between I and J there's a finite distance. So if you were to pretend that it wasn't centered on H but it was centered on J, it looks exactly the same. I is now two units of distance away from J, K is 2 units away, L is then 4 units away. Or if I was to center myself on M, L is now 2 units away, N is 2 units away. Every single letter on this number line, the universe around it looks exactly the same. And then if we go to the third line, it's still the same fact. Every piece of this in this scenario, immediately after the Big Bang, it was also infinite rather than tiny, but extremely dense. Yeah, so I think the next thing I wanted to get into in the stream was talking about what one means by the beginning and after the Big Bang. But yeah, I mean, in this scenario, it was at some point in the past infinite, but extremely dense. Yes, I think going back to the sort of singularity where things get um, uh, infinitely dense is another thing where it's just becomes sort of speculation. But yes, so I'll just share your screen, Paul. Share your comment, share your screen, present on screen. Yeah, so at some point of time, let's say when these primordial elements were being formed, the universe was already infinite but extremely dense. And so there's no center to this universe. No letter is privileged every letter is seeing exactly the same local stuff that is a certain distance apart, and yeah. So then the other question that I think often comes up in the context of what is the what is happening at the edge, like what is the universe expanding into? So here it's not expanding into anything, it's just infinite and stuff's getting further apart. Then the question is like, where's it expanding from? So here, okay, in my diagram it's expanding from H. um, but if I was K, if you think about what would happen if I shifted everything over so that K on the second row was below K on the first row and K on the third row was below K on the first row, then this would look exactly the same as the centering on H. And so given that the actual overall kind of motion of this line, the bulk motion of the line is an unobservable thing, it's not it's not true to say that the expansion is happening from H, because if I was K, if I saw the universe from K's perspective, I would see H moving away from me and me stationary at the center. Or if I was M, I would see K moving away from me and me stationary at the center. And so the question, so this is maybe my hope behind this is that when people ask the question, where is the universe expanding from? And the answer that people give is everywhere. Like, where did the Big Bang happen? It happened everywhere. It's like, well, like, how could it have happened everywhere? It must have happened somewhere, and now we're moving away from it, or whatever. The idea I wanted to get across in this is it really is happening everywhere. That it happened at M, and M saw H moving away from itself, and it happened at H, and H saw M moving away. That in the past, H and M were very, very close to each other, and they weren't necessarily where H is now or where M is now. They were just close together, and depending on who you are and what perspective you have, it's it's going to be that it happened where M is or it happened where H is. All that matters is that H and M were close together, not where they were, because that location is all relative. So for us, yes, the Big Bang happened where we are. Like, everything that is moving away from us in the past was much, much closer to us. And at this point where we are, the Big Bang happened. And then from their perspective, we were much, much closer to them. And we moved all the way over to where they are, and well, came from where they are. But neither of these perspectives is requiring the other one to be false, because this overall bulk motion of the entire universe is an unobservable thing. So that is what the expansion would look like if it was infinite. I mean, this is what the expansion looks like even if it's not infinite. If it wasn't infinite, it would just be that outside of this sort of one-dimensional number line, there is some boundary, or if it repeats, you get back to A. If you travel far enough to the right, you get back to A again. This is what the local expansion looks like, and this is why, yeah, the universe can still look homogeneous despite being expanding, because it's not that everything's moving away from H and it's unobservable. Sorry, and it's noticeable that it's expanding from H, because any other letter, the universe moving away from it looks exactly the same. So yeah, getting from that to the question that you asked Paul a few days ago of is there more reason to believe the universe is finite or infinite? In terms of raw empirical fact, no. There's no reason to believe either is more correct. Um, in terms of models of the early universe and how compelling they are, okay, now we get into personal preference, and I can tell you what I find compelling, but that's not fact. That's just personal preference. So one can't talk about the early universe and models without getting into inflation, because it's the most commonly studied early universe model. And one can't talk about inflation without having to worry about this concept called eternal inflation. So I prepared some figures to talk about internal inflation. So inflation is da, 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 this paradigm where the laws of physics allow a situation where if the energy density of the universe is close to constant. So what I've got here is a potential energy function. This is the potential energy as a function of some field phi. So a field is a thing that takes a value everywhere in space. You can have a temperature field, you can have a velocity field where everywhere in space material has some velocity, it's moving in some direction. So this is a a field. This would be the inflationary field, and it has an energy density as a function of its value. And then the universe would take some value of phi, and then because of that, you would get some energy density at that point in the universe. Every different point in the universe would have a different value of phi, and therefore a different value of the potential energy. But in this part of the potential energy on the left, you see that the potential energy doesn't change much with the value of phi. And if this was the case, you get the laws of general relativity, the laws of gravity allow this inflation, which is an accelerated expansion, where the objects in the universe move apart from each other with an accelerated rate. With just ordinary matter or dark matter, you would get things moving apart but decelerating, which is exactly what one intuitively expects, because gravity is normally attractive. It should be that even if you've got an enormous amount of inertia and you're moving apart, gravity should be slowing you down. But the laws of physics allow that if there's this exotic material that has an almost constant energy density in space, and which is possible by having this almost constant energy density in space and time, sorry, which is constant, which is possible by having this flat region of the potential energy function, you can get this accelerated expansion. I'm not going to go into details today in this stream about why that might happen, but what is crucial about this picture here is if it's sufficiently flat, I've drawn this gray band, and what happens in eternal inflation is that the field wants to roll down to its minimum. So what that means is if I'm at some point in the universe such that the field takes some particular value of phi, the laws of motion of that field, the same way that the law of motion of a car on a hill is for it to want to roll down, the law of motion of this field is that at that point in space, it wants to take a smaller value of phi, and it would evolve to a smaller value of phi and release that built up potential energy as kinetic energy, that phi will now be changing in time, which will have some energy. So that's where the energy has gone. But quantum fluctuations in this field phi will push it equally in either direction. Now, what happens is that once it gets to what I've labeled here as phi e, which is phi end, is that inflation would end. So if at some point in space phi has evolved to the point where it reaches this phi e point, inflation will end, and then you would get this normal decelerated behavior as the universe is expanding. But in some other part of the universe, the quantum fluctuations might have left it further up the potential. And in fact, if it gets into this gray band, the idea is that the quantum fluctuations pushing it sometimes up the potential will be faster than the gravitational evolution of it rolling down. And that would mean that even though some patches of the universe reach this phi e and then have what we would call the hot Big Bang, where you get the projection of hydrogen, helium, lithium, you get your cosmic microwave background, you get your galaxies, you get your people, some other part of the universe is still inflating. And so it's hard to get something flat enough to support an inflation that could generate our universe without accidentally producing a region of this potential energy function that can support eternal inflation. And so probably my personal best answer to your question, Paul, of is there more reason to believe the universe is finite or infinite, is that there's more reason to believe it's infinite, because of the fact that if inflation is true, eternal inflation is difficult to avoid. And if eternal inflation is true, then you would get that even if our isolated Big Bang has happened for us, some other part of the universe is still at this very large, very rapidly accelerated expansion phase of eternal inflation. And then you get something that looks like this next picture, where you get these bubble Big Bangs, the yellow stuff, but outside of it, you get something that's inflating. And this red stuff is accelerating in its expansion and expanding much faster than the yellow stuff. So more of the universe, the total universe, is in the red stuff. And there, I guess it gets into a question of exactly what one means by the universe being finite and infinite. if one means at a fixed point of time, could, if one was, God or the person simulating the universe, if you could stop time and just move further and further away, maybe in that sense, the universe is in some sense finite. You might get to some edge, or some repeating thing. Uh, in the real universe, you can't do that. As you're traveling, the universe is getting older, in which sense it it is infinite in the sense that you would never get to an edge. The further you go, the longer time has been going, the more this eternal inflation has just been causing everything to expand, and the eternal inflation will last forever, unless there's some other law of physics that causes some, there's some other field that is evolving in some way that messes up uh, this idea of this potential energy function. Maybe there's some other field that is slowly evolving and changes the shape of this so that eternal inflation ends. But as far as we're aware, you know, I've been in the realm of speculation for a while now in this chat. As I said at the very beginning, all we know is for sure is the observable universe that's expanding into more universe. That's very much finite because of this finite time, finite speed of light thing that we can only see a certain distance away. But yeah, eternal inflation suggests that at least the following statement is true. If you wanted to say some minimum size of the universe, I could tell you a minimum time you needed to wait, and it would be bigger than that. So it's always going to be possible to find a time where the universe is bigger than whatever one wants it to be. The other thing, perhaps, that one could mention here, it's not about finite versus infinite, but just about overall size. Inside this kind of toy diagram I drew earlier, where we have our observable universe and the rest of the universe. Inside this observable universe, this circle that I've drawn, the universe is extremely homogeneous on average. There's no part of the universe that has more galaxies or fewer galaxies. The cosmic microwave background that we're seeing right from the very, very edge of all of this is very uniform in its temperature. In fact, yeah, that plot that Deanna Hooper, the other cosmology streamer on HAPS, likes to show, as I've said, is not actually the cosmic microwave background. It's the cosmic microwave background anisotropies, which are only 1 part in 100,000 of the actual temperature. So the fact that this whole bubble we're in, this whole sphere that we can see of the observable universe, the fact that it's so identical everywhere suggests that at the very least, the part of the universe that looks like us, that is expanding like us with the same temperature as us, is a lot bigger, because it would be a remarkable coincidence that today, in October of 2021, the finite size we happen to have been able to see is the very edge. Like, why today's no special time. So it seems far more likely that because things aren't changing dramatically inside the universe, that the observable universe, that outside the observable universe, it still carries on the same for some large distance, maybe 100 or 1,000 at least times this central circle before one would start to see something different. But if something like eternal inflation is true, it would be infinite. You would never be able to get outside of the expanding bubble that we're in. You wouldn't actually be able to get to the edge and see this eternal inflation piece. You just see inside of our Big Bang. So I hope that is in some way enlightening and helps helps you feel that the question was partially answered. Yeah, so we covered where is the universe expanding from, which is sort of everywhere. Actually, just briefly, this idea that the universe is homogeneous is why we know. I'm just struggling a bit. Is why we know. There we go. Is why we know that we're not, for example, in something like a white hole scenario, which is this time reversal of a black hole. That if a black hole sucks everything in, a white hole would spit everything out. You might say, well, white hole would look like it's expanding. How do we know we're not in a white hole? A black hole very much does have a special point, the center of the black hole, and things are falling into that point. They're not doing it in such a way that everything's homogeneous. There is a point and there is a spherical symmetry around that point, but there is not homogeneity everywhere. So we know we're not in a white hole because we see everything expanding in this homogeneous way, not in a very special way. There's not some special point where things are expanding from. So I thought that was an interesting side point. Right. I don't know if I want to get into did time really come into existence at the beginning. Can I talk about anisotropies? Yeah, sure. In what specific way? Do you mean like what the word means, Arthur, or I guess maybe I'll just anticipate that that's what you're asking. So anisotropy means not isotropic, and isotropic means the same in every direction. So cool. So and something that is isotropic looks exactly the same in whichever direction you look in. Whether you're looking north or south or east or west, or if you think about every angle on the sky we could look, if it was perfectly isotropic, it would look exactly the same in every direction. So this cosmic microwave background, which is the thing that formed when in the very early universe neutral hydrogen formed, the universe cooled enough that the electrons bound to the protons, and then that light was able to travel for the rest of the universe's history until we detect it now with our telescopes. That is extremely isotropic. It has a temperature of about 2.7 Kelvin, I think. And the anisotropies, so when you look at different angles, the slight differences in the temperature of this cosmic microwave background are of the order of microkelvin. So micro being 10 to the minus 6. So when you, yes, so they're 100,000 times smaller than the temperature of the actual cosmic microwave background. So that's when I think when I was talking earlier about anisotropies in the cosmic microwave background or in something else, that's sort of what I'm talking about. So those things are interesting because they can be used to infer what that early universe was like, what the tiny fluctuations in its temperature and density were. And then because they're so small, they're very easy to predict. If you have a given cosmological model, you can say what they should look like. And therefore, by measuring them, you can say, is my cosmological model correct? You can constrain what certain parameters in your cosmological model should be, and things like that. So I hope that uh, that answers your question. Let me know if not. So I think I had another one planned of did time really come into existence at the start of the Big Bang? But I think that sort of mm, the answer is essentially sort of the same thing, that once we get above this nuclear physics energy scale, we don't have any direct evidence of anything in the universe's expansion. And once we get above the energy scales of something like the Large Hadron Collider, where we've studied physics pretty clearly and we see what's happening, we aren't able to even know what we should predict for what the early universe should look like. So yes, you do get, if you assume that the universe is made up of stuff that looks just like radiation, where radiation is the same as light or just very quickly moving matter, you get a point of infinite density within a finite amount of time. This is the infamous singularity. Now, if one takes that to its absolute conclusion, then you can't go earlier than that, because if you go earlier than that, the mathematics is broken. You've got an infinite density, you don't know what to do with it. But and it might have been that like 50 years ago, this was kind of the expectation that the universe, that was the dawn and creation of the universe. But in reality, we have absolutely no idea. Once we get above the Large Hadron Collider energy levels, we don't know what the universe is made of. And there's no reason it has to stay as radiation. And if something like inflation is true, it doesn't, right? Like once you get to a large enough energy scale that, as I was showing in that plot before, which I'll bring back up now. Yeah, definitely, Paul. When I say above an energy scale, I mean above a certain density. It's energy density that is the relevant thing here. Did I click present on screen correctly? I guess not. No, yeah, I did. Okay. Should be presenting soon. There we go. it's energy density that's relevant here, not mass density, right? So mass is energy in special relativity, but energy is also energy. And in general relativity, it's energy that seeds gravity, not just mass. So mass seeds gravity because it is energy, and energy seeds gravity because it's energy. So it's energy density. It's the total amount of joules of energy inside a unit volume that is the relevant unit here. So when I say above an energy scale, yes, I mean energy density scale, amount of energy contained within a certain volume. Yeah, which then relates to something like the Large Hadron Collider, because when you're firing protons at each other, those protons have a certain amount of energy, which would translate in the early universe. There's some time when, if a proton was around, it would be traveling with that same energy because there's that much energy in its volume to give it that much energy. Yeah, and so if inflation was true, just putting this image back up, then at some point in the past, there's enough energy that the inflaton field is on this plateau. At the moment, I mean, in terms of current energy scales, we're so far into this minimum of the energy that these inflationary energy scales are enormous. They're billions and billions of times larger than our currently probable energy scales. But if you run the universe backwards, eventually you get to that point. And then the universe isn't dominated by radiation, it's dominated by this inflationary field. And then you get a completely different time evolution of the size of the universe, of the density of the universe as a function of time. So I think to talk about, as some people do, the am I back? Yep. As the start of time is just assuming that it goes radiation all the way back to this infinite density. But like the number of factors of 10 in energy scale between us and infinite density is infinite. So there's all sorts of crazy physics that can happen in these earlier times. So I find it very. There are speculative theories about how, I think it comes under a kind of wave function of the universe kind of language, where yes, the universe and time and space came into existence at the beginning of the hot Big Bang or the Big Bang, but I don't think it's anything but speculation in terms of observation, and it's not necessarily even super compelling. It's possible that the universe is infinitely old in that sense. Just like because of eternal inflation, it would be infinite into the future. It may have been infinite into the past. And we are just the consequences of some patch of this infinitely old universe getting an inflation field up into that plateau such that eternal inflation could start. And you got all of these little bubble Big Bangs that I showed you earlier in like this schematic picture. And that there is no beginning of space and time with this initial singularity. Yes, it's possible there was a singularity and that this wave function of the universe idea, which I would have to go into another stream because I'd have to learn about it in a lot more depth before I could do it justice. But it's also possible, yeah, that some patch of the universe, of the distant past universe, excited this inflationary field, eternal inflation, and started, and you started getting these bubble Big Bangs, and we just happened to be in one of them. So I think, this idea that time started at the beginning of the Big Bang is presented more factually than observations allow it to be presented. The observationally true part of the Big Bang is observationally from this nuclear synthesis, the formation of things like hydrogen, helium, and lithium onwards, and then the stuff that we can make very trustworthy predictions about is up to the Large Hadron Collider energy scales, and the stuff that we can maybe make slightly more accurate speculative predictions about is the oh, thank you, Paul. Happy Halloween. Yes, the early universe is very spooky. Is maybe inflation. There are observational consequences of inflation, and we can observe them. But certainly, once one's talking about inflation, one doesn't need to talk about an initial singularity, because the expansion of the universe during inflation being exponential means that it actually doesn't reach zero volume or infinite density in a finite amount of time, which is I don't know, maybe that would be a tangent that is too far, but during a radiation dominated period, so if I lose everyone for the next 30 seconds, then I apologize. We'll bring everything back. But during a radiation dominated thing, the density of the universe follows a polynomial function of time. And so therefore, if I just set t to 0, I have an infinite density. Whereas during inflation, it follows an exponential period of time. So then if I set t equals to 0 in an exponential, where the density is some function of e to the power of time in some way, then it's just finite. And in fact, even to the infinite past, it's still finite. Although there are issues with the infinite past of inflation that I'm not going to get into, but it probably didn't have an infinite past for subtle reasons. But at least it didn't reach a point of infinite density in a finite amount of time. Okay, that's an hour. So if people still have some stamina, we can carry on. I wanted to talk about two more things, but I think I'll leave the multiverse one for today because I don't know. We'll see what my stamina is. What does it look like inside a black hole? So here is another one of my attempts at a. Where do I think the research in the inflationary theory will held in the next couple of years? I guess you mean what will it blah, 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 what will it presenting? Come on. Yeah, where it will head. That makes more sense. In the next couple of years. Well, a couple of years is a very short period of time. Probably not very far. In modern cosmology, 2 years is not a lot of time because observations are so difficult. Uh, so, what would be really interesting would be a detection of these primordial gravitational waves. That I think Arthur, you arrived a little bit late, but right at the very beginning, I was talking about a paper that had not detected primordial gravitational waves, which means it had just set an upper bound on how large the energy density could be during inflation. If one was to detect these primordial gravitational waves, it would tell us the energy scale of inflation, and that would allow us. It is. I'll find a link to it. Just a sec. I'll try and multitask as I'm doing it. It would. No, I can't multitask. But here's the link. It's a very technical paper, so I'm not sure if you are yourself a cosmologist, but if not, you might not find it easy to digest. Yeah, if we were to measure this energy density of primordial gravitational, well, if we were to measure this amplitude of primordial gravitational waves and therefore energy density of inflation, we would be able to open up a kind of idea of what inflation was like, and then you could measure how these gravitational waves change with distance scale. Do they have a bigger amplitude on one wavelength and a smaller amplitude on another wavelength? Things like that would be very interesting. Without that, I can't anticipate any dramatic changes in the next couple of years. The main work that seems to be being done in inflation at the moment is um, looking for ways to learn about the paradigm as a whole and as model independent a way as possible. In fact, I think if you go to my first ever sole stream on this platform, I was talking. I think the title of the stream is something like uh, "The Early Universe in as Model Independent a Way as Possible." So actually, yeah, maybe instead of me just repeating myself, go and watch that stream on Haps or YouTube, and get an idea of get an idea of how that might might be the research that's being done, trying to learn by imposing certain fundamental kind of laws like causality that things must follow a causal path. Something can't precede its cause. You can infer what the early universe must be like, and then from that you yeah. I didn't prepare to talk about that, so I'm blanking a little bit. And also, I saw that there was a comment on YouTube, so I wanted to address that. So, Bhargav Anim asks, "Can I talk a little bit about the utility of the illustrious TNG simulation in new research?" Yeah, very very briefly. I mean, I'm not an expert on that, and it wasn't sort of on the topic I'd prepared. But illustrious TNG is a very big simulation of the universe, including these hydrodynamical effects. So comparable to this Thisan project I was talking about right at the very, very beginning. But yeah, having such a large box that also has these hydrodynamical effects is a really crucial thing. A lot of these simulations that include hydrodynamical effects are like simulations of isolated galaxies or isolated galaxy clusters, which is still a huge distance scales compared to us. But compared to the size of the whole observable universe, these are often quite small, like 1,000 times smaller, perhaps. What's useful about Illustris TNG and Illustris in general is that they tried to get as large a box as possible so that you can start to do genuine cosmology. Thank you, Mark, for the great discussion award. You can start to get blah blah blah. What was I saying? Cosmological facts out of your box, whilst also having the correct small scale hydrodynamical physics of gases and stuff. So, at least for today, that's all I can say, Bhargav. But if you're super interested in it, I can try and get someone from Illustris to maybe have a stream, because they certainly are very I don't know, important. Their simulation is a very important thing for modern cosmology, as perhaps Thesan will become. Maybe Illustris is no longer important because these new guys have possibly made a bigger, better box. Right. So on the main agenda, getting back to that, we have what does it look like inside a black hole? Right. The answer to this is actually really simple. It doesn't look very different to what it looks like outside of a black hole. But that might surprise people who have read a little bit about black holes, because it's also a true statement that once something crosses this event horizon of the black hole, and I assume that when people are asking what's it like inside a black hole, they mean inside the event horizon. I'll talk about what the event horizon is in a second for people who aren't familiar with that. But once you cross the event horizon of a black hole, you will inevitably reach the center of the black hole, where again you have a kind of infinite density problem. So I can see how it might be very puzzling how in one sentence I can say inside the black hole it won't look very different to outside the black hole, but also anything that has crossed the event horizon of the black hole will in a finite amount of time reach the center, that there's no moving away from the center, that all paths inside the black hole lead to the center of the black hole. And the reason why I think that it is confusing is there's this idea that what if okay, so let me just briefly talk about what a black hole and an event horizon is. The event horizon is the radius away from the center of a black hole at which nothing can escape. If you were on the event horizon or a tiny, tiny little bit inside the event horizon and you shined a light beam away from the black hole, it will fall into the black hole. If you're just outside the event horizon and you shine a light beam directly away from the black hole, it will gradually and eventually escape the black hole. So that's what this event horizon is. That's what the special distance away from the center of the black hole is. So then, yeah, maybe it sounds quite confusing. Like if let's say there's two of us falling into a black hole, and you're slightly further in front of me on your falling into the black hole journey, and you shine a torch at me, and I'm telling you, and this is a true statement, that I will see the light come from that torch, and then you're like, well, hold on a second, Sean, you literally just told me that everything is falling into the black hole, that nothing can get further away from the center of the black hole. So how will you see this torch? Surely once you've crossed the event horizon, everything's going into the center of the black hole, and you shouldn't be able to see the light from the torch because it has to move away from the black hole to get to you. How can these two statements be consistent with each other? So I've kind of drawn here, you've got the center of the black hole, you've got this event horizon, then you've got this box, which is supposed to be a box of stuff falling in. And then I've zoomed into the box. Now, inside the box, what you would see is nothing unusual. You would see this dot that is emitting light, and the light would go in every direction. What is the crucial missing piece here is that this box, this reference frame that you're in, is moving towards the center of the black hole, or accelerating towards the center of the black hole very, very quickly. So anything that is moving with the box will be able to see light moving towards it, but that's just because everything is moving towards the center of the black hole even faster. So if you were to be plotting the distance from the center of the black hole of the light as a function of time, it is always getting closer, but it's getting closer more slowly than you are. Therefore, you overtake it. And so from your perspective, you just see everything normal. You just see someone shine a torch, the light comes to you. The reason why everything is normal is that, well, I say normal. I mean, you'll get funky visual effects from far away. Like, I mean, I'm sure I'm not sure, but you might have seen the things in this movie Interstellar where you look at the black hole and you see the very beautiful. I should have got an image of this to share, but you see this very beautiful kind of image of light being bent around the black hole. So certainly when you're near a black hole, things from far away can look really, really interesting. And it would still be the same inside the black hole. Light that's coming from far away will have been bent in all sorts of wacky ways. And you will see very funky images, but it won't be different just inside the event horizon as it will be just outside the event horizon. And certainly as you get closer and closer and closer and closer and closer to this very center, stuff will start to look very, very wacky as the lensing of light gets much, much more extreme. And then the natural question is like, what happens at the center that you're going to reach in a finite amount of time? And there I have to go back to what I was saying about the early universe, that at some point the gravitational effects become so extreme that one is expecting general relativity to no longer be relevant. And at that point, you just have to say, we don't know, and either go into a black hole with a very precise measurement equipment and you'll know the answer, but you won't be able to share it with us because we're not inside the black hole, or wait for theoretical physics to catch up, and we can talk about what might happen near the center. But at the moment, in pure general relativity, it will reach an infinite density in a finite amount of time. What actually happens just before the end, we don't know. But yeah, have I threaded the needle well, in the sense that this picture now makes sense without apparent contradictions, that everything is moving towards the center of the black hole, you can't move away, that a light emitted just inside the black hole will travel towards the center of the black hole in a finite amount of time, but it'll just travel there more slowly than something else, and therefore that something else will catch up. And therefore the idea that if you are freely falling into a black hole and you're playing a game of tennis on your spaceship with your friend, the tennis ball is not going to suddenly, as you cross the event horizon, just zoom away from you towards the center of the black hole. It's still going to go over the net. You're going to be able to play backwards and forwards in a totally uninhibited way. And the real funky stuff won't happen until you get to the very, very center. So that's what it looks like inside a black hole, the same as it looks like outside of a black hole. Cool. I think I might call it a day there. The multiverse stuff we can get to another day. Thank you everyone who was here. Thank you Arthur and Paul for asking questions. Thank you Mark for the great discussion award, and Paul for the Happy Halloween award. The next stream will probably be at this time next week, although I have noticed that there weren't too many people here, and I have done a few streams on a Friday in the past and there were more people, so I'm not sure whether it was just the topic, or because maybe people who come to these streams don't want to hear answers to frequently asked questions. They want to hear new stuff. So probably the same time next week, Arthur, but potentially a different time depending on what I think. If you subscribe or follow, I forget what the technical HAPS term is, then I think you get notifications when I schedule, and I won't just start streaming, I'll schedule a few days in advance at least. So yeah, you can find out that way. Yeah, if you want to catch more streams in the future where the streams will be more about what the actual researchers are doing, then come along next week. I think next week, I can't promise with 100%, but I think what I'll be talking about is a paper that has measured the stuff that is called baryon feedback. That is this idea that on the very small scales, things like supernovae and black holes are doing all sorts of crazy funky stuff, and it's very difficult to predict what you will expect the universe to look like on these small scales, which is why you have things like Illustris doing their simulations. And this this makes it difficult to learn about what the cosmologically interesting things might be on those small scales, how much dark matter there might be, what the initial conditions that cause that might be. So one way is certainly to do lots and lots of simulations and try and actually predict, given the cosmological parameters, what those small scales could look like. But another way is to also find clever ways to measure what the supernova rate and other things might be on these small scales, and then use that to constrain what it looks like, and therefore have a more clear prediction of what the cosmologically interesting things might be doing. So that's what this paper did. It looked at a thing called the thermal Sunyaev-Zeldovich effect, which is the scattering of the cosmic microwave background of hot gas. So if you're keen on learning about that and how by doing that they were able to learn about the primordial fluctuations in the density of the universe more accurately than you would otherwise, then come along next week, because that's what we'll be talking about next week. Other than that, thanks everyone for coming, and see you next week.